Okay, this video covers three major topics. It starts off with the definition of what is a function, and we'll talk about a few different examples of how to identify a function. Also, it's going to talk about what the domain and range of a function are, talking about inputs and outputs, and trying to get us thinking in that function mentality, because that's what we'll think about mostly in Algebra 2. And then finally, we'll also talk about what function form is, and how you can use function form to make a simple graph or do various other things. So first of all, on this main screen, you've got the definition of a function. Basically, for every input, there has to be exactly one output. And think of a function like a machine. It's just like this big black box over here. Basically, if we just take one thing and we insert it into the machine, what happens is we're only going to get one thing back. I'm not going to be able to pull multiple items out of my machine, and notice there's nothing else to pull out of here. It's not really grabbing anything. For every one thing you put in, you get one thing back. A lot of times we'll represent a function using a relation map, which is what we have down here. The domain of a function is the set of all of the inputs. So turning the key or inserting quarters and pressing a button or doing homework, those are all things you would do as inputs in order to get something back. The range is the set of all outputs. So all the things you would get back, or the result, those happen in the range. So if you turn the key, your car might start. Or if you insert quarters and press the button, well, you might get a soda pop. And if you do your homework, well, you should earn points. Now you could also do other things like take a test, right? And those could also earn you points. Realize that this is still a function. For every input, for every one thing that we put in the domain, they went to exactly one thing in the range. It doesn't matter that two of the items went to earning points. Each of the individual things in the domain went directly to one of the items in the range. Now, that's the main idea behind how we represent what is a function. So what you want to do is take a good look at the two mapping relations here and identify which one of them will be a function. And if you said that option A was correct, A is a function. Every item in the domain goes directly to one item in the range. It doesn't matter that one of the items in the range wasn't used. It also doesn't matter, again, that these two items in the domain went to one item in the range. 2 went one place, 3 went one place, and that's what really matters. What's wrong with relation B? Well, B is not a function because item number 4 in the domain heads to two different places in the range. One item in the domain should not have two outputs. Every input has exactly one output. That's the definition of a function. Take a good look at these tables and decide if x's are the inputs, if x is the input and y is the output, which one of the three tables represents a function? If you said that option A doesn't work because it's got two inputs of 5, then you're correct. 5 should not go to two separate places. Option B also can't work because 2 is headed to two different places. Option C almost has that same issue, except for that 2 goes to 4 and 2 again goes to 4, which is perfectly okay. Really, you just don't need that twice, and therefore option C would be a function. Now, when we talk about function form, that's how you determine from an input how do you get an output. And when we see this notation that says f parentheses x, you can read that as f of x, or the value of f at x. When we plug in a value for x, we want to know what the output is. And your f of x is the function of x. So x, for this first one, is just going to become a 2. So on the right side, where 7 is multiplied by x and then subtracting 6, what we're going to do is we're going to plug in 2. So 7 times 2 is 14, minus 6 is 8, and there's your output. We could say that the function of 2 or the function of f, I should say, at 2 is 8. Or if you wanted to make a coordinate point out of that, when you plugged in 2, you got 8. Do the same for the next 3 below there. Go ahead and pause the video and fill in your answers. Alright, hopefully you just wrote down the exact same phrases that I did. 7 times 8 is 56, minus 6 would be 50. So again, the output is 50. Input 8, so domain contains 8, range contains 50. At negative 3, that makes for negative 21 is negative 27. And 7 times 0 is 0, minus 6 would be negative 6. So again, all the numbers on the right side here would represent the domain, or the range, the outputs. All the numbers that you plugged in for x, 2, 8, negative 3, and 0, would represent the domain. Do the same again for the function on the right. Once again, I just rewrote the function. So negative 2 times parentheses plus 5. And I did that for each of our functions here. And then took out the x and plugged in my inputs. So this one became 2 and 8, negative 3, and 0. When you find all those numbers, you should have ended up with 1, negative 11, 11, and 5. Again, the inputs being your domain, outputs being your range. Now, how can we use that kind of idea? Well, you might be used to graphing a line on a coordinate grid. Remember, x-axis is traveling left and right, y-axis up and down. Your quadrants start out as 1, 2, 3, and 4, traveling counterclockwise. And if we make a table from our equation, we're basically just plugging in. We're saying find y when x is. And for the 4 values down here, when x is negative 1, well, 3 times negative 1 minus 5 is going to give you negative 8. And I can plot the point. Input, output, negative 1, negative 8, down here on my graph. Do the same for the other points. So at 0, we're down at negative 5. For 1, we're at negative 2. And at 2, we're up at positive 1, up in quadrant 1. Now we could continue to do that, although hopefully you see the pattern that we're going up 3 and right 1 each time, so I can continue to draw my graph. We'll talk more about graphing in a future lesson. The big thing I want you to realize is that instead of saying y equals, you could actually refer to this as a function, f of x equals. And therefore my inputs were x's, my outputs are f of x's. And you've drawn the entire line to represent your graph so that we've got this nice line traveling through our points. Don't forget your arrows, as technically it would infinitely travel onwards. And also realize, don't forget to label your axes. So where this was the point at 2, 1, I can label this line a 1, this line a 2, or I could go out to the edges and say, well, this was 10 and 10, telling me that I counted 1 per each line. That's how you can graph a function. The other thing we want to be able to do is, again, identify what is a function. If we can identify it from a relation or a mapping or a table on a graph, how can you tell what is or is not a function? And for that, remember, for every input, there should be exactly one output. Or for every x, we need exactly one y. Well, on a graph, if the x-axis is traveling left and right, and if you remember about vertical lines, that their equations are x equals, the vertical line test would tell you that for every x, or every time that we grab this vertical line, if I can grab it here, we might just have to draw our own. But every time you would draw a vertical line on a graph, the question is, will it pass through more than one point? So on this graph, if I move that vertical line left and right, do I ever pass through more than one point on my black line? And the answer to that is no. Which means for every x, there was exactly one y. And yes, that one's a function. Let's go ahead and get rid of our question so yes isn't confusing there. We'll just say, is each graph a function? Well, if you draw that vertical line again through this one, if you moved it left and right, again, we would never hit more than 1 point. And the same idea goes if we go over here. Now, some of these points look pretty close, like right in here, but realize that if you follow that line, it does keep moving to the right as it goes up and down. It keeps going back and forth. So therefore, yes, again, this line passes. Same thing goes for this nice curved line. As you move a little bit to the right every single time, it's going to pass a vertical line test. And yep, that one's fine. The one that doesn't, however, is if we draw that vertical line here and here, no, we hit more than 1 point at a time, and therefore that can't be a function. So the option E is not a function. Last thing I want you to do is just practice a little bit. So take a second, pause the video. For the graph on the left, list off the domain and range. Take a look at the points and give a list of which points, what numbers, since this isn't a straight line, can't use all the x's and y's, but which ones would fall in the domain, which numbers would fall in the range. Also, tell me, is it a relation, a function or not? And then practice a little bit with finding points. Find in function form the value of f of x when x is 0, 3, or -2. Again, pause the video and I'll put up the answers. Alright, here are your answers for you. All I did was took a look at all the points that are on the graph, such as the point 2, 1, right here. And remember that the x value is going to fall in the domain, so right here. And the y value is going to fall in the range. You might notice that only 4 numbers appear in the domain. That's because 2 of the numbers repeated. The number at 2, -3 means that the number 2 only needs to be in the domain once. Whereas the range, there are 5 different y values. Those 2 points also are the reason why that this is not going to be a function, because those 2 points fall on the same vertical line, or for that one input, they have 2 different outputs. So not going to be a function. On the right, you've got your 3 answers over here, 0, -3, and 22. Make sure you take a close look at the squaring portion, because if there are any mistakes made, my guess is it probably happened there. But if you check your work, hopefully it turns out well, and good luck on your homework.